What specific problem does your proposed visual memory aim to solve in the context of deep learning, and how does it differ from existing approaches?
The proposed visual memory aims to address the limitations of static knowledge representation in deep learning models, which struggle to adapt to changing data requirements and new information without retraining. Unlike existing approaches that embed knowledge within model parameters, our visual memory separates representation from memory, allowing for flexible addition and removal of data, such as through machine unlearning and memory pruning. This system enables models to incorporate new out-of-distribution classes without retraining, maintaining performance on existing classes while achieving high accuracy on new ones. Additionally, our visual memory facilitates improved decision-making through innovative aggregation methods like rank voting, which enhances classification accuracy by effectively utilizing retrieved memory samples. Overall, this approach provides a more dynamic and interpretable framework for managing visual knowledge in deep learning.
How does the proposed visual memory mechanism work? Please illustrate the methodology step by step, detailing how images are retrieved and classified using this memory.
The proposed visual memory mechanism operates through a two-step process, building a visual memory and performing fast nearest neighbor-based inference. First, a visual memory is constructed by extracting feature maps from a pre-trained image encoder, like DINO-V2 or CLIP, for a dataset of image-label pairs, creating a database of these features and their corresponding labels. When classifying a query image, the feature map for the query is extracted using the same encoder. The system then retrieves the k nearest neighbors from the visual memory based on cosine distance, which ranks the neighbors by their similarity to the query image. Finally, the labels of these neighbors are aggregated using a weighting strategy, such as the proposed rank voting, to determine the most likely label for the query image, allowing for effective classification without retraining the model.
Can you provide a simplified example detailing how your rank voting aggregation method improves classification results compared to existing voting methods?
The rank voting aggregation method improves classification results by assigning weights to neighbors based on their rank in the ordered set of retrieved neighbors, specifically using a power function weight formula. W_i equals frac1 alpha plus text rank _i, where alpha is set to 0 to avoid division by 0. In contrast, existing methods like plurality voting assign equal weights to all neighbors, while distance-based and softmax voting methods can overemphasize distant neighbors, leading to performance decay as more neighbors are included. Our experiments show that rank voting consistently outperforms these traditional methods, achieving better accuracy as the number of neighbors increases, indicating that it effectively integrates information from relevant neighbors while mitigating the influence of less reliable ones. For instance, when comparing the top 1 ImageNet validation accuracy, rank voting demonstrated a performance increase with more neighbors, while traditional methods plateaued or declined. This highlights the effectiveness of rank voting in leveraging the most pertinent information from the visual memory for improved classification outcomes.
What are the primary theoretical or practical advantages of using your flexible visual memory system over traditional deep learning models, particularly regarding the addition and removal of data?
The primary advantages of our flexible visual memory system over traditional deep learning models lie in its ability to seamlessly add and remove data without the need for retraining. Traditional models require extensive retraining to incorporate new classes or modify existing labels, which can lead to catastrophic forgetting. In contrast, our visual memory allows for the flexible addition of new out-of-distribution OOD classes while maintaining in-distribution accuracy, as demonstrated by the integration of 64 new classes from the NINCO dataset with minimal impact on existing performance. Additionally, our system supports efficient machine unlearning, enabling the removal of specific data points from the memory without degrading model performance, which is a significant challenge in conventional models where knowledge is embedded in millions of parameters. This capability not only enhances adaptability to changing data landscapes, but also preserves privacy by allowing sensitive data to be stored separately in memory.
What validation or testing methods did you employ to assess the performance of the visual memory model, including the datasets and metrics used?
To assess the performance of the visual memory model, we employed several validation methods using the ImageNet validation dataset and the NINCO dataset for out-of-distribution OOD testing. We measured top 1 accuracy as the primary metric, achieving 88.5% accuracy on the ImageNet validation set through our rank voting aggregation method, which surpassed previous state-of-the-art methods. Additionally, we evaluated the model's performance on various OOD datasets, including ImageNet A, ImageNet R, ImageNet, Sketch, ImageNet V2, and ImageNet Real, to ensure the robustness of the visual memory across different data distributions. The experiments also included systematic analysis of neighbor reliability and the impact of different aggregation strategies on classification accuracy, demonstrating the effectiveness of our retrieval-based approach. Overall, these methods provided a comprehensive evaluation of the visual memory's capabilities in both in-distribution and OOD scenarios.
What are the limitations or challenges you encountered with your visual memory approach, and how do you propose to address them in future work?
The primary limitations of our visual memory approach include the reliance on a fixed pre-trained image encoder, which may restrict the adaptability of the model to new data distributions or concepts. Additionally, while our rank voting method improves performance, it may still be sensitive to the choice of parameters and the quality of the retrieved neighbors, which could affect classification accuracy. Future work could focus on enhancing the encoder's adaptability through continual learning techniques, allowing it to update its representations as new data becomes available. Furthermore, exploring more sophisticated aggregation methods beyond rank voting could help mitigate the influence of low-quality neighbors and improve decision-making reliability. Lastly, integrating mechanisms for dynamic memory management could enhance the model's efficiency in handling large-scale datasets while maintaining performance.